This question was asked in the GATE Physics paper 2021. This is a numerical answer type 2 marks question, and this question was asked from the topic quantum mechanics. The question is, the normalized radial wave function of the second excited state of hydrogen atom is r as a function of small r equals to 1 by root over 24 e to the power minus 3 by 2 times r by small a times e to the power minus r by 2a, where a is the Bohr radius and small r is the distance from the center of the atom. The distance at which the electron is most likely to be found is y times small a. The value of y in integer is, so basically you have to find the value of y such that the electron is most likely to be found at the distance y times a, where a is the Bohr radius. So let us see how to solve this problem. The general form of the hydrogen atom wave function is given by psi nlm as a function of r theta phi in spherical polar coordinate equals to multiplication of two function. First function is rnl as a function of small r, which is radial distance. So basically this function is radial part of the wave function, and the other function is ylm as a function of theta and phi. So this is known as spherical harmonics, which contains the angular information of the wave function. Here n is the principal quantum number, which can take the values 1, 2, 3 and so on. The L is orbital quantum number. Depending on the n value, it can take the values 0, 1, 2 up to n minus 1. And the m is magnetic quantum number, which is represented as ml because its value depends on the L value, and the values it can take, ml equals to minus L plus 1 and so on. It can take maximum value up to L. Now we will discuss about the normalization condition for the hydrogen atom wave function. According to the normalization condition, the integration over entire volume, that is integration over r, theta and phi of the wave function mod square times the elemental volume, that is r square sine theta d theta dr d phi equals to 1. Now this wave function psi nlm is multiplication of two part, that is radial part rnl and the angular part which is spherical harmonics, that is ylm. So we'll put that, we'll get integration over r theta and phi mod of rnl square and mod of ylm square times r square sine theta dr d theta d phi equals to 1. Now we'll separate the radial part and the angular part in this integration. So we'll get integration from r equals to 0 to infinity of r nl mod square times r square dr, and the other part is the angular part, that is integration from theta equals to 0 to pi, integration over phi is equal to 0 to 2 pi mod of ylm square sine theta d theta d phi equals to 1. Now we'll concentrate on this radial part only. So here this term, that is mod of rnl square r square, this term is denoted by pnlr. So this pnlr, which is mod of rnl square and r square, is known as probability density function at radial distance r. So we will see why it is important in our case in the next slide. So the probability that the electron in hydrogen atom would be found between the radial distance small r and r plus dr is given by the probability density function, that is pnl as a function of r times the dr equals to the mod of rnl square, that is the radial part of the wave function, times r square times dr. Now in our question, the normalized radial wave function of the second excited state, that is the principal quantum number equals to 2 in this case of the hydrogen atom, is r as a function of small r equals to 1 by root over 24 times e to the power minus 3 by 2 r by e times e to the power r e to the power minus r by 2e. Here is the bore radius. Now, if we want to represent this radial part in the formal way, that is R in L form, so basically it will be R21 because it is the wave function for second excited state. So N will be 2 and L can take value either 0 or 1. Now we'll not discuss it much from the, I mean, we can only say here from the solution of the Schrodinger equation, we can get the R21 function is this. Now, the probability density function P21 in this case, mod of R as a function of small r square times r square, where r as a function of small r is given by this. We have to find the most probable value of small r, which is radial distance, or the value of small r where the probability of finding the electron in the hydrogen atom is maximum. Now we'll consider the most probable value of r is Rm. So at r equals to Rm, the probability density function, that is P21 in our case, will be maximum. So at r equals to Rm, the derivative of the probability density function P21 with respect to small r will be 0. So we'll put the expression for P21 in this equation. Now P21 is basically mod of R21 square times R square. Now mod of R21 square is 1 by 24 times a to the power minus 3 r square by a square times e to the power minus r by e times r square, there is a term. And then we'll take these constant values, so that is 1 by 24 e to the power minus 3 and here 1 by e square out of this derivative. So effectively we'll get the derivative with respect to small r of r to the power 4 e to the power minus r by e at r equals to Rm equals to 0. So we'll just do the derivative here. So we'll get 4 Rm cube times e to the power minus Rm by e plus Rm to the power 4 times minus 1 by a times e to the power minus Rm by e equals to 0. So we have done the derivative of this function. Now we'll take this Rm to the power 3 times e to the power minus Rm by e as common, and remaining term will be 4 minus Rm by e. So from here we can conclude 4 minus Rm by e equals to 0, since the remaining part Rm whole cube times e to the power minus Rm by e not equals to 0, because Rm cannot be infinity or Rm cannot be 0. So electron cannot exist within the nucleus, so Rm cannot be 0 in this case. Also Rm cannot be infinity, it should have some finite value for having the most probable value of R. So from this equation we can say Rm equals to 4a. So the most probable value of R is Rm equals to 4a. So our y value in our question is y equals to 4. Now we'll discuss some important tricks to solve this question very easily. So the first point is, if the radial part of the hydrogen atom wave function is proportional to e to the power minus r by Na, then we can directly say the principal quantum number for the wave function is n. So in our case, the wave function radial part was for the second excited state, so n equals to 2. Now, if we know the principal quantum number for the wave function, so we can say directly the probability of the finding electron is maximum at Rm equals to n square e. So in our case, n equals to 2, so the most probable value of Rm is 4a. So this shortcut formula we can apply to find the solution of this question. We have already solved this problem, and also we have discussed some important tricks which will be very useful to tackle this type of problem very easily. And we found that the answer of this numerical answer type question is 4. So the distance at which the electron is most likely to be found will be 4 times Bohr radius.